In the last lecture, we talked about some of the basic properties of light. In this one, we're going to look at some examples where classical physics fails and this new idea, this need for quantization, emerged. So we're going to look at a few examples, in particular something called blackbody radiation, the photoelectric effect, and atomic line spectra. So while classical physics proved enormously successful for describing things like electromagnetic radiation, for baseballs being thrown through the air, and so on, it turns out it's not actually sufficient to describe everything in the universe. Things like atoms and molecules at the very smallest scale actually cannot be well described by classical physics. But in the late 1800s, it actually seemed like most of physics was a solved problem. There were just these few edge cases that had emerged that people didn't understand. For example, blackbody radiation, this idea that really hot materials can emit light. You've seen this, for example, in molten lava, as the picture shows here, or perhaps in hot iron, how it turns red and eventually white hot. Atomic emission, which is the principle behind neon signs, for example, or the photoelectric effect, where light can cause electrons to be emitted from a metal surface. As we'll talk about in the next several slides, none of these could really be described by the classical models of the day. To begin, let's talk about blackbody radiation. So again, blackbody radiation occurs when objects emit light upon heating. This graph here shows the distribution of wavelengths being emitted by a blackbody at different temperatures. So for example, if our blackbody object is at 2500 Kelvin, it emits light according to this distribution of wavelengths, with a maximum emission in the infrared around 1200 nanometers. As that object is heated up further, however, the emission shifts further toward the visible until by 5500 it's peaked somewhere around yellow and green. And so this explains why, for example, iron gets red hot or lava emits red, because those have hot temperatures in which there's a significant amount of emission in these regions. Now, if you try to describe blackbody radiation in terms of classical physics, you can derive a model that works well in this region at large wavelengths. However, it performs very poorly at short wavelengths. Instead of showing this maximum that's observed experimentally, you instead see predicted emissions lines that go up towards infinity as we get to shorter wavelengths. This is what's called the ultraviolet catastrophe. It would predict that there's infinite intensity of light being emitted at short wavelengths. Obviously, that's not correct. And it's important to stress that this error is not an error in the person deriving the model, rather it's a fundamental flaw in the laws of classical physics. So Max Planck, right around 1900, managed to finally solve this problem with an unusual trick. So he started off modeling the blackbody radiation as arising from a set of vibrating atoms that emitted energy in the form of light. This is pretty similar to how everyone was modeling it in those days. However, the key unique feature he added was that he assumed that the vibrational energies could only have certain discrete energies, so that the energies had the form of the frequency, depending on the frequency of which the atoms were vibrating, times some constant, h, times an integer n, where n could be 1, 2, 3, 4, etc. And so this is this idea of quantization of energy, that there's only certain allowed values of energy that can occur that are these integer multiples of h times nu. Now this h is an empirical constant that Planck fitted to the experimental data. And when he did so, he got a value of 6.626 times 10 to the minus 34 joules times seconds. We now call this Planck's constant. So the interesting thing here is, with these assumptions, Planck was able to derive a model for blackbody radiation that reproduced the curves I showed you on the previous slide beautifully, but it just wasn't clear why he had to make this assumption of quantization, why we had only these certain discrete energies that could be allowed. Next, consider the photoelectric effect. This was another problem that defied classical physics explanations. So the photoelectric effect is this idea that if you shine light on a metal surface, you can sometimes cause electrons to be ejected from that surface. Now, according to classical physics, the key factor governing whether the electrons are ejected and how fast they move when they are ejected should depend on the light intensity, its brightness in other words. However, in reality, the intensity didn't control either of those factors. What mattered was the frequency of light, not the intensity. Einstein was the one who actually managed to solve this problem, and he did so by borrowing Planck's idea. And so he proposed that what if instead of light arriving at the surface as continuous waves, continuously delivering energy, what if light arrived in little packets of energy as what we now call photons, and that each photon had a certain amount of energy associated with it, and that was what caused the liberation of the electrons. And so in other words, this is the first instance of something that we're going to talk about more in future lectures called the wave-particle duality. That in addition to the wave-like behaviors of light that we talked about in the last lecture, that it can also have a particle-like behavior in the form of photons. So the basic idea is that each photon has an energy h nu associated with it. Or, using the relationship that nu equals c over lambda, you can rewrite that as hc over lambda. So the brightness of the light determines the number of photons, but not the energy delivered by each photon. Rather, the energy of the photon depends on the frequency. Now, the electron in the metal is bound by some certain amount. The metal has some certain force holding that electron in place. We call that the work function phi. But again, it's just how much energy is holding that electron to the metal. So if the photon's going to eject the metal, it has to have enough energy inside that photon to be greater than the work function, greater than the amount of energy that's holding the electron in place in the metal. And so if that photon has just enough energy equaling the work function, then it will just barely be able to break the electron free. If the photon has more energy than the work function, it has some excess energy, well, that excess energy will get converted into the kinetic energy of the electron that determines how quickly that electron flies away. So in other words, the kinetic energy of the electron leaving the metal is going to equal the energy in the photon minus the energy of the work function. Basically, how much energy was left over after we used some of the photon energy to liberate the electron from the metal. And if we plug in h nu for the energy of the photon, we get the kinetic energy is equal to h nu minus the work function. So the picture we have here is, for example, that a red 700 nanometer wavelength light might not have enough energy to liberate an electron from a particular metal. So we shoot the surface with that wavelength and no electrons are ejected. However, if we shorten the wavelength to 550 nanometers, now we have a shorter wavelength, a higher frequency, a higher energy. Now maybe we have enough energy to liberate that electron from the surface. We have more energy than the work function, and the excess energy goes into the kinetic energy of the electron. And so that electron leaves with, say, this 2.96 times 10 to the 5th meters per second velocity. If we go to an even shorter wavelength of light, 400 nanometers, now our photons have even greater energy content, and so that electron is going to get ejected with even more kinetic energy because there's going to be more energy left over in the photon after it liberates the electron from the metal after overcoming the work function. Fitting to experimental data, Einstein found that this H constant had the exact same value that Planck had found, which was pretty remarkable, right? Here's two completely different problems, blackbody radiation and the photoelectric effect. They both made some assumptions about energy coming in packets, this quantization of energy, and they both derived the same value of this constant H. So this caused people to pay attention. This said there was something fundamental going on here that wasn't understood. Let's go ahead and do some practice problems. So which of the following statements regarding the photoelectric effect is true? No, more than one of these statements may be true. Go ahead and read these statements, pause the video, think about your answer, and then we'll discuss the solution in a moment. So let's take a look at each of these item by item. So A, increasing the brightness of the incoming light increases the kinetic energy of the ejected electrons. That's false. The brightness determines the number of photons arriving, but it doesn't determine their kinetic energy. B, increasing the frequency of the incoming light increases the kinetic energy of the ejected electrons. That's true. The frequency is related to the energy content of the photon. So the higher the frequency, the greater the energy. The greater the energy, the more that's going to be left over after overcoming the work function, and therefore the greater kinetic energy you'll have in the ejected electrons. C, increasing the brightness of the incoming light increases the number of ejected electrons. That's also true. The brightness determines not the energy content of each photon, but it controls how many photons are hitting the surface. So if we have more photons hitting the surface, we're going to have more electrons ejected, assuming those photons each have enough energy to cause an electron to be ejected, to overcome the work function. And finally, D, increasing the frequency of the incoming light can increase the number of ejected electrons. That's false. The higher frequency means you have greater energy content in the photon, but any excess energy gets converted into the kinetic energy of the ejected electron. It doesn't cause multiple electrons to be ejected. Let's try another question. Sodium metal has a work function of 3.65 times 10 to the negative 19th joules. Will a 650 nanometer photon eject an electron from sodium? Go ahead and try and solve this. And again, hit resume when you're ready to hear the solution. All right, let's take a look at this. So what we want to do is we want to figure out how much energy content is in our 650 nanometer light, and if that amount of energy is greater than or equal to the work function. So the energy content of a photon is related to h nu, or hc over lambda, if we substitute nu equals c over lambda in the expression. And so we can go ahead and work this out. So because we're given our wavelength here instead of a frequency, I'm going to use the second form, hc over lambda equals energy, to plug in here. So I plug in Planck's constant, I plug in the speed of light, I plug in our wavelength. But our wavelength is in nanometers, so I need to convert that wavelength from nanometers to meters, using the conversion factor that 1 nanometer is 1 times 10 to the minus 9 meters. Which I do here. When I multiply all this out, my meters cancel, my seconds cancel, and I'm left just with the units of joules for energy, and I get 3.1 times 10 to the minus 19 joules. Now this amount of energy is less than our work function, right? It's 3.1 times 10 to the minus 19 versus 3.65 times 10 to the minus 19 joules. So this wavelength of light does not have enough energy per photon to eject an electron, so no electrons will be ejected. Therefore, it's answer D, no, because it has energy less than the work function phi. Finally, let's talk briefly about atomic emission spectra. So it turns out atoms can emit light at certain distinct wavelengths, and the emission spectrum actually provides a fingerprint for a given element. Have you ever wondered how we know what elements the sun is made of or other stars are made of? We do this by looking at the emission spectra coming from them, from the light being emitted by the elements in these stars. And so, for example, you can see that in hydrogen we have very certain discrete frequencies being emitted by the hydrogen atom, and these are different from the frequencies being emitted by a calcium, a mercury, a sodium, etc. And these are very different from the continuous spectrum we see throughout the range of visible light. And so there's this question, why is light only being emitted at these certain discrete frequencies? It's again some form of quantization. I'm not going to talk about the solution yet because we need another lecture to do that, but we'll return to this point in the near future. But it's going to be a third example where quantization of energy is fundamental to the nature of the system, just like blackbody radiation and the photoelectric effect. So, to summarize, we've seen once again the importance of the interrelationships between the energy, the wavelength, and the frequency of light. Last lecture we saw that nu is equal to c over lambda, frequency equals the speed of light over the wavelength. We now understand that the energy content is equal to Planck's constant times the frequency. We've seen that light can exhibit this wave-particle duality, meaning it can act as both a wave and a particle. We've seen examples of the wave behavior, the two-slit experiment, for example. That is clearly wave-like behavior with the interference pattern being generated. At the same time, it can exhibit this particle-like behavior with the photons and the photoelectric effect, where the energy is coming in these discrete packets of light rather than as a continuous wave. Third, we saw that this idea of quantization of energy is required to explain blackbody radiation, the photoelectric effect, and atomic emission spectra, and actually many other things. This is a key idea that we've introduced that we're going to come back to and see, and it really forms some of the fundamental basis of chemistry.